I'm going to talk about generative adversarial networks, or you can call it GANs, depending on your preference. I prefer to call it GANs because it has adversaries, so sound like you are killing some people. That goes well with the academic environment, really. So moving forward, so we have seen that it has three parts: generative, adversarial, network, of course, is neural network. That's fine. So let's first talk about the first thing, which is the generative part. All right? So what really happens there? So when you typically talk about deep learning, using deep learning, convolutional neural networks for object detection, segmentation, whatever, you are typically looking at the discriminative problem. So finding decision boundary or boundaries if it's a multi-class problem, or even more difficult situations. But typically it's about finding the decision boundary between labeled images without considering much about the process of those images generated from. So that's where the generative part comes in, and the idea there is that if you maybe can able to generate realistic looking images, then it might be one step closer to understanding how these images are generated. And if you are one step closer to that understanding, that might be a helpful thing in the general context of computer vision, image analysis, even in medical imaging situation. But this is, again, a very pedagogical talk. So this is more about taking the advanced concepts and trying to blend into intuitions that you can hold on to while you are looking through your research steps. So the first gross approximation you can think of whenever you are taking up a paper and seeing, okay, it has GANs or CNNs or whatever, is basically take a look at the output. If the output looks something like a classification, a class, then most likely it's a CNN paper, versus if it looks like something of an image that came out, more likely it's a generative process. This is a bad gross approximation, but gross approximations are there for that reason only, because it works for most of the cases. For the rest, the exceptions, you can still go on and study more about the paper if you are feeling intrigued. All right. Now, at this point, I have about 80 more minutes. And you can either go into your smartphone and look at there, or you can listen to what I'm saying. So the point really is, why would you listen to what I'm saying? So one of the things that happened that makes my talk probably a bit more interesting is if you just look at the sheer results. The results look quite amazing. Okay, so started about with these super resolutions. So you can see here bicubic, which was the state of the art before the CNN came in. That was doing roughly a smoothed out version of the actual image. And now with the GANs, you can see a lot of these details are retained. You can also do something very cool with cycle GANs, for example, which are basically doing style transfers. So you just take an image taken by your smartphone and just try to convert it into how probably Monet or Van Gogh would have drawn it. And those things you can do with your cycle GAN. Awesome. And probably you have also seen some of these images. Most likely, if you are going to another talk about GANs, people are going to ask which one is real, which one is generated by images. Most likely the answer are all are generated by GANs. So none of these are actual images, none of these are real people, these are all fake and generated by some method out of some random numbers. So that's quite cool to start with. All right, but this is medical imaging. This is nothing to do with computer vision. So the next question is, of course, what is in it for me? I'm not going to hear you for 80 more minutes to talk about some cool looking face images of people. That doesn't make sense. So medical imaging is also quite building up in that. So I will go into more details about the applications. But here I have just shown or sampled two of many possible applications of GAN in medical imaging. One is trying to reconstruct CT from MR images and doing it in a way so that you don't expose the patient into a lot of harmful radiations. You can do it. Or you can go into finding the anomalies in your data without having to do specific annotations. So in an unsupervised way, you try to figure out where the disease is located. So those kind of things are possible to do with GANs. All right. So imagine now for a second that GAN is not something of a developing technology, but it has achieved some success. It has actually become of a technology that's reusable and that provides you results again and again you try in different applications. Then what you can do really. So let's try to anticipate for a few moments what it can actually help you out with. One of the things that it can do is that it can be used as a proxy for training data. At least some of us like to claim that. There are no perfectly proven truth about it, but this is one of the things where GAN can be most useful in medical context. So for example, all of us know how difficult it is to do annotation in the medical context, especially if you are trying to do all those localization, pixel by pixel annotation. That's a whole different mess. And GAN might help you out there by generating these proxy data for which it also provides you some form of annotation. There are also imbalances in whenever you have your medical data coming out. There are significant imbalances that's there, and how you deal with that, probably GAN might help you out in those cases. Then it has already been shown that this adversarial training part, this adversarial component of GAN, can be used as a successful metric. In one of the Mukhopadhyay 2018 paper on registration, they have shown that while trying to do image registration, instead of using a particular metric attuned to solve that problem of how similar the two images are after registration, if you just use the adversarial training framework, that might do a pretty nice job as well. And finally, there is this problem of domain shift. So you train your things into one particular domain, and then you go into a multi-center data, or you have probably 6 different MR acquisitions, and one of the protocols change, 5 remain same, and then suddenly nothing works anymore. Until, of course, you have also annotated data for the target domain where you can transfer learning it. Then it's perfectly fine. But imagine if you don't have the opportunity of getting annotated data in your target domain, then GAN might be helpful. And then I will show you one example where such a thing has already been done. All right. So probably after getting your first attention, why you should listen to me, now let's talk about how I'm going to talk for the rest of the part. This GAN or this basically GAN idea, and I have tried to do it. I could have done it in many different ways, but I have chosen to do it in Marie Kondo way. Okay, so those of you who are familiar with Marie Kondo, that's perfectly fine. Those of you who are not, you will be familiar. There are no people who will be living in this world who doesn't know about Marie Kondo. But the idea here is that she is someone of a tidying up guru. Okay, and what she tries to do is she tries to show some ways you can tidy up your entire home. That means tidying up your closet, your kitchen, whatever. So I took that idea, and I'm trying to tidy up GANs to a way so that it becomes a bit more accessible, easily accessible for those who are starting to explore GANs. So basically we have our closet here, which is our theory, the key GANs that's going to be used. And that's a lot of mess going on there, so I will try to clean it up a bit. Then comes kitchen, where you have your medical applications. So most of you, since coming from medical imaging, so that's literally what brings food to your plate. So that the kitchen is probably the right metaphor for that. And finally, the emotional part is something where I'm talking about guns and I should only talk about the awesome things, but there are also limitations. So that's sort of emotional from my side, where I will show you the things where it doesn't work, where you should be careful, where you should not believe what I'm trying to sell you for the next 60 minutes or so. All right? Cool. So let's move forward. So theory. So what Marie Kondo said is, let's bring out all the things that's there in your closet, because most likely you have just put it there, all your clothes you take out and put it there, and it's a mess there. So let's first take those out and create a heap out of it. So I will try to create that heap out of it for you so that the theory becomes clear then. All right. So we start with the simplest of the theory, where you have a black box, G, which is your generator. It takes as input some Z, and it predicts the image, which is G of Z. Okay? So that input can be something that you can sample very easily. For example, a seed that comes out from a multivariate normal distribution. And out of it, you try to use some form of functionalities that's there in the black box to create your image. All right. But that actually is associated with a bigger problem, and we can call it basically perplexity. So it's basically a way to critique G so that you know whether it's getting better or getting worse, right? So what perplexity does, it's basically a probability density function of the generated distribution. So that means if you pass an image through it, it can tell you how likely it is that that particular image is generated from G, from the black box. Now, how to deal with such perplexity and what are the ways to solve it, that's a whole different topic for another day. What I am going to tell you today is how GAN sidesteps it. So there are 3 key twists that GAN uses to sidestep the entire perplexity mess. All right? So these are the 3 ideas of those twists. So the first one is basically use a deep net, and then use a gradient feedback, and then you make it a game theory of many moves. All right? Too many things again. So let's try to break it down piece by piece, small pieces, and let's try to explain each of these. All right? So the first thing is how you are going to be sidestepping it. So, and this is exactly, so it's a lot of theory going on here, so I will try to make it slow and make it accessible, and so that we can probably talk about it in more easier details. So basically you have these 2 different probabilities, probabilities of the real images and probability of the synthetic images from which these images are generated. And what you are interested in then is basically you are interested in finding a deep neural network, D, that maps those images in between 0 and 1. All right? So what's really going on here? So the interesting part is that then what your D is necessarily trying to do is trying to look at images that's coming from the real distribution and making the expectation of those as high as possible. Whereas those images which are coming from the synthetic distribution, you are trying to keep the expectation as low as possible. All right? So D necessarily is basically someone who is making sure that it can separate images from real and synthetic. All right? And then you can basically, since it's a deep neural network, you can train it with backpropagation. All right? So what was supposed to be the job of perplexity, now we have found a deep neural network that can solve it for you. And because we know deep neural networks are so awesome, so maybe they will do a good job or okay-ish job in solving it. The next thing is gradient feedback. Now, we also have a generator, right, that actually generates these synthetic images. So what's really going on for that generator is that it generates synthetic images, but if it is just any random image, it's not going to be something which is really meaningful. So the job of this generator is basically make sure that the expectation of this is as high as possible. That means you take the Z, you create the synthetic image, and you pass the synthetic image inside your D, and you try to make sure that the EZ, the expectation that it's coming from this, is as high as possible. That means you are trying to make sure the synthetic images have similar expectations as your real images. Okay. All right. And then, of course, you can also, so this basically means you are trying to fool the discriminator into believing that what is your synthetic images is actually not your synthetic, but the real ones. And you can, of course, backpropagate all the way from D to G and come back. So you have backpropagation of D, and you have backpropagation of this combined network of D and G together. Now you can make this a game of many moves. So you try to train G, which has information about D, and of course it also generates. And you can train D, which has no information about what's going on inside G. It only sees the images that came out of G, and it tries to predict whether it's real or fake. All right? So probably let's take a moment to see this, because this is an image which I'm going to show you again and again. So every time you feel like, okay, what's going on? So we can come back and look into this image, and we see all the motivation, all the moderations that made out of it. But this is the basic image on which everything started. All right? Now once we have this thing, next look at the objective. All right? So the objective can be the following. So we try to, of course, make this as high as possible. So we have a maximization of D. And then we want to make this also as high as possible. So we do 1 minus this, so that this is a minimization of G. And then together we have, so as long as F is something which is monotonically increasing, you are fine. Your life is fine, and then you might get probably into a nice little approximate minimum of yours, which would solve your purpose. The problem, though, is that what should be your function? Now you can imagine that once you have the possibility of using more or less many possible monotonically increasing functions, there is a whole really research going on in the theory field of what should be the best function that does the job for you. But let's look at what originally was proposed by Ian Goodfellow. So he proposed to take fx as log x, and that basically solely because of the reason is that if you take the derivative of log x, it takes 1 over x. That basically translates in the common English to you are very sensitive to instances that D finds awful. So you look at all the images being generated synthetically by your generator, and you look at the most awful ones and penalize your objective for that. All right. There are also GANs, for example, called Wasserstein GANs, where they have chosen f as simply x, fx equals x, and that basically means you don't penalize to one particular things, but you penalize all of them equally. All right. So that's more or less the mess of theory that's out there in front of you. But probably right now your idea is, okay, so that's a lot of theory. What's going on? What's really the interesting thing from a medical imaging perspective? So let's go back to Marie Kondo again. So what did she say? So she said, once you have such a mess, you keep only those things that brings joy to you, and you stack them in a proper way. So I will try to do that. Okay. So what really brings joy out of this is basically trying to find an engineering recipe. So you really probably are not that much interested into going into the theory, finding the right sort of functions, what takes the derivatives, but a sort of engineering recipe that can help you out in navigating those engineering zoo of GANs and probably look at some of the medical imaging papers as well from that perspective. So the engineering recipe is quite simple. We have our input-output, we have our architecture, and we have our loss function. Those three together are more or less enough to give you a first intuition. I'm of course not saying that those things which are going on inside, they are not important. No, that's not my point. But really my point is, if you are trying to appreciate at both levels, the details, and at the higher level, you are probably going to be missing a lot of interesting things. So let's first try to understand the higher levels, and then probably we can go into and look into the more detailed part and see what sort of things were chosen for a particular job. All right. So here I will first introduce you three key gun architectures that's been proposed there. The first one is DC gun. The second one is C gun, the conditional gun, and the third one is cycle gun. So again, nowhere I'm claiming to be exhaustive. That's not really my point. My point is to give you some intuitions about these key gun architectures. There are some more architectures which you might also tell me that those are key. Yeah, I completely would agree with you, but the point is I thought these are important enough for this talk. All right. So let's first then look into what DC gun did. So this DC gun basically took more or less the same thing that Ian Goodfellow proposed in his original work and tried to show actually how this can be implemented in the convolutional neural network settings. So DC means basically deep convolutional, and then gun is gun. So what's going on here is that in this paper they are trying to generate in an unsupervised fashion the representation of the images. So they are trying to learn the representation image, trying to learn the representation so that they can actually generate realistic looking images. All right. They have also introduced something which is quite interesting, and people have used it again and again across many different papers. It's called latent space interpolation. So the idea here is the following. Imagine you have a deep neural network of millions of parameters, and you have a 2000 sample data set to train your network from. More likely, it's possible that your network just remembers those 2000 samples and nothing in between. So it didn't learn any representation. It just remembered how those 2000 samples should look like. How do you make sure that that's not the case? It actually learned the representation. So what they did, they basically considered 2 points, 2 seeds in your multivariate normal space, and tried to see if they interpolate from one of these seeds to another, how that interpolation would be translated in the image space. So here you are seeing that you basically started with random numbers and you interpolated random numbers and you got a very nice smooth transition of, in this case, bedrooms. All right. So that's quite a nice thing. That gives you an idea that, okay, so in between these are not random cases, but it has actually learned a transition. So coming back to my recipe, we are now looking at the input, output first. So what's going on there? So the input is Z, which is a 100-dimensional multivariate Gaussian, and output is the image. Okay, quite nice. Now let's look at the architecture. The architecture, I said they kept exactly the same thing. So you have a generator, you have a discriminator, it takes Z as input, creates an image which is synthetic, and you get real image, you predict real effect. Now let's take a closer look at what's going on in the generator. So the generator basically looks like this, where what you can really see is that this is your input, which is a 100-dimensional Z. And from there, you go ahead all the way to create GZ, which is your image. Why it's 3? Because these are color images, so it has RGB 3 outputs and then this is the 64 by 64 image that they are creating. And as you can see here, they are basically trying to do deconvolution at different steps and trying to reach all the way to the image that they are generating. And the loss function is more or less same as the one proposed by Goodfellow. Moving forward, now let's look at what is called conditional GAN. And here the idea is that complete unsupervision is probably not too realistic or not really something that you are going to be looking for. Because whatever data you are using, you might have some information associated with it. And you can use your data generation with that kind of conditioning. So for example, here in this case, I have shown the MNIST digits, and you probably know what classes they are coming from. But it might not be like that. Maybe you are looking at a database of faces, but for those faces, you don't know the exact personality from whom it's coming, but you still have some more general viewpoint of those faces. So maybe it's like whether it's a Caucasian or a brown skinned man or someone who is coming from a dark skin background, whether he or she is wearing a glass, whether he has some hair or he is blonde like me, stuff like that. So those kind of, I was looking at who was listening to, whoever didn't get the joke, I wish you'd come back and get the joke again, maybe in the video. So the point really is that those sort of conditions are there in the data sets, most likely or more likely than not. How you can bring that kind of conditioning. So again, if we look back into our input-output, we can see that you have Z, and you also have associated with it another input, which is the condition. This can be, for example, if you are trying to deal with MNIST, you have 0, 1, 2, stuff like that. And then here you are looking at these images with the correspondence. Now let's go into the architecture. In the architecture, we basically are looking at then Z and the condition coming in as input to your generator, and then you are getting as output the image that is generated. You also have the real images and the condition associated with it, and you are trying to predict real or fake. You might also be a bit more creative and think of, rather than just predicting real or fake, we can probably predict some of the other things that's coming out of here. All right. So those are really different choice of possibilities. And if we now look at the loss functions, it looks more or less the same. Only the thing is now you have conditional here, and that condition is basically the C that's coming out from your design choice. All right. But that's nice that for each image, even though you don't have probably the right kind of exact annotation that you looked for, but you have some idea of annotations that's coming along with the images. What if the more crazy case? So the more crazy case is something where you are trying to do style transfer, right? And you are trying to incorporate unpaired images for style or domain transfer. So the examples that comes from the cycle GAN are just trying to horse into a zebra. Now imagine you are trying to learn it. It's unlikely that a zebra would pose the exact same way that your horse image is taken, so that you have pixel to pixel correspondence and you can learn things. Probably the zebra is in a completely different kind of body shape and structure than the horse. And then even if you take a lot of horse images, a lot of zebra images, it's unlikely that the background remains the same. So it's a very more open, unconstrained problems. And how are you trying to solve it? It's the same of when you are trying to turn an apple into an orange. Or even more obvious is the case when you are trying to take as input the images that you have taken with your phone and getting as output how Monet would have drawn it. Monet would never come and draw for you an image of the exact same image that you have taken with your cell phone. So that's really an unpaired case. You might have some set of images taken by you on domain X, and another set of images drawn by someone like Van Gogh or Monet, and you are trying to transfer the style of your image to Monet's way. Now that's a very, very challenging problem for obvious reasons. There are many, many different ways of transferring such styles. But these guys have come up with a very interesting approach for doing this, for solving this problem. What that approach is? So they basically came up with the idea that let's look at the cyclic consistency. So basically, instead of one generator and one discriminator, they have two generators and two discriminators. So what's really going on here? So let's first try to deconstruct this into a more understandable version, which is this. So you have two different domains, X and Y. So your smartphone, Monet, and your smartphone image is passed through G to look something similar to Monet. And then you again pass it back to another F, which is another generator, and you just turn it back to how it would look like in your original smartphone way. So what's the idea here? The idea here is the following. So I am here where I know exactly how I look like, or my smartphone image look like. And then I go to another domain of which I have no idea. Sure, you can't put any loss on how much things have changed because you don't have exact pairs. But if you try to come back from that domain back to yours, you should look same. If you don't look similar, then you can measure how far away you are from your original space. So let me give you another example. I am an Indian. I am now living in Germany. If I go back from Germany to India, will I be not Anirban, an Indian, but am I someone else? If I am someone else, that means there is a problem of this transition. And that problem is something that we are trying to measure. Ideally, I should go out and come back as the same person, unless I have changed my nationality. That's a different story for another day. But for this one, that's the exact idea. And you do the exact same thing there. So you don't know if you take an image drawn by Monet and try to show it how it would look like if you have instead taken it with your cell phone. Okay, no idea. But if you just get back from there to the Monet domain, it should still look like the original painting. All right. So now let's look at a summary of what I have talked so far with my engineering recipe. So we have talked about three different key gun architectures: DC, conditional, and cycle gun. And then we look at each of these, how the images are taken. Typically, the input gets different, output remains similar, unless here where you still get an output, an image, but it's from a different domain. If you look at the architectures, it gets progressively more and more interesting, but it's still something which is recognizable if you look at the blocks. The problem of this is that if you really look at the papers and try to not look at the block design, but actually what's going on inside it as a CNN, then it gets way more complicated, way less decipherable. But if you really try to look at the block designs of the entire architecture and what's coming in, what's going out, it's probably still something that you can easily decipher. Then once you build your intuition at this level, of course you can go ahead into the details and try to figure out what's going on there. That's always there. The losses, we can see the original one is the gun, then this one is a slight modification of gun with the conditioning, and when it comes to here, it still had all the previous losses, and then you also add the cyclic consistency on top of it to make sure things are done well. This is unsupervised, conditional, supervised, and then style transfer here. These are kind of the application areas that you look at. So again, the idea here is that when you receive your new medical imaging application problem, you really try to think of it for a second, just step out of the exact details of the doctor who is not talking to you, and really look into what really are you gonna be solving. If it is solving just image generation, then you can do one thing, versus if it's really solving a style transfer, you do another. If you have a different sort of biases in the data, maybe you should think of doing some conditioning to get more data out of one particular distribution. These are still open choices, but this gives you the possibility of thinking more in an intuitive way of the problem that you are trying to solve. So before I move on to the actual medical application part, any questions so far? Yeah.
Just for the conditional GAN, if you can just go back please to the next, previous slide. So Z and C, they are just concatenated at the input of the, when you put these two lines? Or is there different ways to input Z and C?
This is more of an open choice, really. Okay. You can do it many different ways, and yeah. It's like, yeah.
And in the standard, in the classical paper of SIGAN, because it was not clear in the paper, I think, what they did.
Yeah.
Is it concatenation or?
Well, the classical SIGAN paper also, what was not probably clear is that they didn't really use a kind of convolutional network as well. They had, I think, a fully connected one, because this came in 2014. So way before all these things started. So it was still right after, I would say, the Ian Goodfellow paper. So it was more about just getting the theory right rather than getting all the actual application of what really works. So, yeah.
And I don't know, maybe from your experiment, what's the best way to combine Z and C?
Okay, so that's a good question. What's the best way? What's the best practice? The problem is it really depends from applications to applications, and it also depends on what sort of data you actually have available. So typically we start actually at the cycle kind of architecture. We don't really do much of the conditional GAN stuffs in our lab, because we are more interested in getting the entire image as input and try to do a style transfer to see what sort of outputs are there. So we try to predict, for example, video frames of the future of surgical videos that's going on, and for those cases really just conditioning on one variable doesn't help much. But probably with your disentanglement it might be interesting. I don't know. What's your take?
And my second question, just maybe to help the audience to understand, in this situation, G for cycle GAN is very different from the G from DC GAN, because G here is an autoencoder, I guess, because the input is an image, whereas in the standard, the first DC GAN, the input is a vector, so it's
yes.
just
so
to make things maybe
absolutely
clearer for the
absolutely
audience.
Yeah, you are completely right. So the G is in essence a placeholder, a block for your generator. What exactly the generator architecture would be depends from your problem to problem or how you are trying to deal with. So one common way is when you have image to image translation is just to consider UNIT as the vanilla start and see from getting one sort of image as in, another sort of image as out, and so UNIT is probably the easiest thing where you can start, and then you try to bring on top of it. Whereas if you just have one number or like 100-dimensional number as your input, then of course it makes no sense to do UNIT. In those cases, you do more of a deconvolution step only. But it really depends on the problem you are trying to deal with. There are cases, for example, when in my lab we were trying to do video prediction, we had a sort of U where on the input side we were taking an LSTM. so that it can encode multiple video frames from the past, and on the output side it was still one image that was coming out, that's the next frame. So there are possible, yeah, but you are absolutely right. It makes complete sense to be very specific that this is just a placeholder and you design based on your problem. Question?
Yeah, I have two questions about the C again. Yeah. Well, why does the C goes into the real data? And also, you can give some examples of what would be a C, a number or a vector?
Well, in this case, if you are looking at MNIST, it can be a number like 0, 1, 2, all the way to 9. If you are looking at something else, it might be a vector. It's really open to the problem you are trying to solve.
And I didn't quite understand why it goes into the real data as well in the scheme.
Why does it go into the real data? This one you mean?
Yeah.
I think that's, I drew wrongly, probably. Because this, I think, comes here, of course.
Maybe for the discriminant part, you can also try to estimate the class. Where's the condition?
Yeah, I think he's asking why it's going into the real image. That makes no sense. I think that's my part of bad drawing rather than anything else. So, apologies for that.
Thank you.
Hello, sir. I have a question about the architecture part. What does the or mean here? Or?
Or basically means you take this and this as input and you are trying to go in and predict whether it's a real image or fake image. So those two are coming in, so we are just putting an or, so that it can take either.
Kind of combined together, or?
If you are doing batch, then you combine together, but you have, typically you don't combine like one sort of, like one fake image, one real image, but yeah, there was some comments. Okay, so you can combine it different way. DC Gun basically said that you don't combine one with the another, but you really do a set of real images and the set of fake images, and then you go in to the next one. Yeah.
Just want to say that the condition, so there was many applications for CGANs, and the reason why the condition goes into the real image is because say you want to generate apple and oranges. So if the condition is apple, so you want the generator to generate a fake apple, but you also want your pool of real images to show real apples, right?
Right,
Versus,
right,
you know.
yeah, okay. So yeah, you are basically
not a
conditioning on the
mistake.
input. Yeah, okay, sorry. My bad again, it was right. But yeah, exactly. So when you are trying to get out an apple here, you want to make sure what's coming in as a real image is also an apple, and you are not comparing apples with oranges. Yeah, yeah.
If it's just a discriminator, why do you have to compare pairs?
No, you don't compare pairs.
So there.
But if you say you want to compare a fake apple with a true apple,
So.
it's a pair of the same class, with the same condition.
Well, there are also possibilities of you make it as like one more step here. So it's like apples, and whether real apple, fake apple versus oranges, whether it's real apple, fake, real orange versus fake orange. Yeah. Question back there.
Hello, sir. I just wanted to ask, like, when do you stop training the network? Means I have read that it's very difficult to exactly understand based on your application at what point you stop training your network.
Okay.
Like the discriminator you're trying to fool, but it's like it's a trade-off. It's a competition, right, between G and D. So at what point do we? Is it by visually looking at the generator output or by monitoring the loss at the discriminator? So that was my question.
Okay. So your question is, when should we stop training? So we were still in the closet pile. You went all the way to emotional pile. Okay, sorry, bad joke. So my point really is that there are no one objective way to figure out when you can say that, okay, I have a finally trained gun. Okay, so you can look at the kind of losses and you try to see when the losses have stabilized. There are also possibilities of actually visually inspecting the images. Some of the these NVIDIA where they showed progressive growing of guns to generate these hyper-realistic images, they train it for 2 weeks in NVIDIA frameworks. So that basically probably answer your question that there is, again, the more computation you have, the more time you have till your PhD you can train. But start with something that starts with a nice convergence. If you see that in the first few steps it's not going anywhere, then probably stop that, kill that, and try something else. Yeah. Okay, if there are no further questions, I probably move on to the right. So now we talk about some of the medical applications. Okay, so this is now moving from closet to kitchen, though we have gone a bit of the emotional part, but let's keep that till the end. All right, so now when it comes to our kitchen, we basically did a recent review of guns that's been proposed there, being published in more or less the top venues, in MICAI, Medal, ISB, TMI, media, stuff like that. And then till the end of 2018, we found about 77 papers that's being published where they used guns for different medical imaging applications. If you look at the distribution of these papers, for obvious reasons, you can see a significantly high number of papers coming into synthesis, followed by segmentation, and then the others are followed. All right. So segmentation, synthesis, those are the two most highlighted things. You can also see some of the registration works really coming up here, and this MICAI, we have seen one of those in the MICAI orals. But there is also quite an interesting pattern when we really looked into these works. And most of these works, of course, they have their internal details of how to make things happen. But if you take a step back and try to look at in these works through the glass of the recipe I was talking about, then most of the works you can think of as modifying the architecture and loss function based on the inputs that you are giving it. And okay, so this is not everything. There are, of course, exceptions. But the good part is that since a seriously high number of these 77 papers actually falls into these categories, for the rest, for the exceptions, you can still go and read the details. So we basically, what I will do, I will try to reapply these recipes on some of these papers. So I have chosen 2 papers from synthesis and 1 from segmentation. But those are just 3 samples. There is a whole lot of work going on there. So again, fair warning, I'm providing here the intuition. It doesn't mean just by listening to this talk you will get all the epsilon deltas of these papers. That's not really the point here. The point is really to see a medical imaging problem and how you can translate it into the gun framework. So the first paper, I think it came in ISB 2018. And there the idea was to discriminate lung nodules between benign and malign. And you are trying to synthesize realistic looking lung nodules. So this is an unsupervised synthesis framework where they try to modify DC gun. So why so? The idea here is that, first of all, annotating these nodules from CTs take time. Plus, once you have such annotations, doing the annotation itself between benign and malign, that's also takes some time. So what essentially you are interested in doing is probably somehow if you can create hyper-realistic looking images of nodules, probably you are one step closer to actually generating training images which we can then use for training our CNNs and get better into that. Okay. They also did a visual Turing test on 2 radiologists. So the idea there was you show these radiologists a sample of real nodules and generated nodules, and you try to see whether the radiologists, the trained ones, can predict which one is real, which one is not so. And that was the interesting part apart from the methodological part of it. But since they talked about modifying DCGAN, so let's first take a look again at the DCGAN recipe. So the DCGAN recipe is the following. It takes as input Z, a 100-dimensional vector. It gets as output 64 by 64 by 3 images, which are these 64 by 64 colored images with this architecture. So what we are now trying to do for this paper, we are trying to see what are the changes. So the first change is that they are giving as input some of these real images, and from this, through this, we are getting some of these synthetic looking images, and we are trying to predict which one is real, which one is fake. All right. So now, and of course, we have the same loss function from DCGAN that these guys also used to train the network. Very nice. Also, what changed is that from those color images, it's lung nodules, so the images are slightly smaller and it has just one channel because it's a grayscale image and not a color image. Now, if we just put the architecture image of this paper that was there in the paper side by side, we can look at, this was in the paper. So the problem of this is that every author or set of authors has their own way of representing things. And if every time you try to read a new GAN paper, it's slightly more difficult to figure out what's going on there. What's really going on here is the following. So this part is the generator part from here, which they are showing the details. And this part is the discriminator part, which is there. And these are showing the details. Okay? So once you have probably such a symbolic representation of these neural networks, it would be a relatively easier thing to solve some of these problems. So that's a unsupervised synthesis of images. How much time I have? Okay, I have some time. So now let's look at the second example, which is supervised images and synthesis of those. So for this, the application really is radiotherapy treatment planning. And what's going on in these cases for this treatment planning, you need to have both MRs and CTs. So MRs for actually segmenting the tumors and the organs, and then CTs are for actually dose planning. So you have to have MRs, you have to have CTs, and you somehow register them so that they are on top of each other, and you plan your procedure. The problem, of course, is that CT means a lot of radiation, and probably any way you can reduce the exposure of patients to that much of radiation is good enough or interesting application. So these authors propose to do MR-only radiotherapy planning with synthesized CT. Okay? The problem, though, is that you have unpaired data. You can put a patient in CT, you can put a patient in MR, you get 2 different volumes, or even if you take slice by slices, you get 2 different slices for the same patient, no registration. You can try to use some of the registration methods to register them. The problem still is that those methods are of course not perfect, and there will be some registration errors that's creeping into your machine, into your framework. So how do you really solve this problem? What these authors suggested is to basically repurpose cycle GAN. because cycle gun is something that can work on unpaired images. So what they did is basically, let's take the cycle gun that I talked about, and then we change cycle gun's input to MRs, output to cities. We keep this architecture where the domain is MR, X domain, and Y domain is city. And then you keep the similar loss functions, but where here you have some of L1 norms at MR and city as your losses instead of the previous cycle loss. Similar idea. Now, if we take a look back at what was there as the architecture in the paper itself. So the architecture in the paper is talking about these two images to explain what they are trying to do. If you now put it side by side, it's relatively easier to guess what's going on here. So they called this as forward cycle. So forward cycle means taking the MR as input, you go through G, generate your city, and go through F, and generate your MR back again. That's your forward cycle. The backward cycle, on the other hand, is the exact opposite. So this is the backward cycle where city is input, going through synthesizing MR, synthesizing back city, and you try to calculate the difference. All right. So it's probably from where I stand, it's much easier for me to figure out what's going on here than looking at these images and trying to figure out what's going on there. And that's again the entire point, that if you have such a recipe that fits to the bill for most of the applications, then it's relatively easier to guess what's going on in the framework. Of course, you still have to go into the details of the generators, the discriminators, to see what sort of activations they are using, what sort of block structures are there. But overall, this is quite simple. All right. And then I will talk about the third application, which is, or the second application really, which is segmentation. Any question before that, though? Yeah?
How do you make sure that the physics of the image that is being reconstructed really fits the physics of an MR or a CT scan?
You don't.
It looks like.
Yes. It looks, and you also can compare the Hounsfield units because you are reconstructing the CT. So as long as they are, like for the soft tissue versus something which is bone, if you have the roughly similar ballpark, you can say.
Yes, but when the physics is drastically different, for example, for MRI, there is trouble in the nasal part that is not existing in the CT. So just coming back to the previous one, there is a big mistake.
Yes.
For the CT.
Yes. So what you are saying is absolutely right. So deep neural networks don't understand the physics of image generation, not yet. So of course it's gonna make mistakes. That's absolutely perfectly fine. I mean, you can probably take it one step further and say it basically tries to match texture to texture and nothing more. And I have some examples which probably gonna give you a shiver that whether you want to really use that kind of reconstruction to generate CT. But that's for later. That's the emotional part. You can't touch that again and again. Okay. Sorry, go ahead.
So you said that this system, you don't need to have paired images.
Yes.
Well, it seems different on this example, but so in case you have pairs, for instance, of MR and CT, what do you think of the difference in performance between using like a UNet, going from the CT and synthesizing the MR, or using such an architecture with GAN? Should the UNet be more performant than?
So the question is whether if you have the exact same pixel-to-pixel correspondence between your source and target domain, should UNet do the trick? The answer to that is probably for UNet you still need to have a metric that measures the generated image and your reality and how far they are. Now, whatever metric you use, that has some good and some bad. So if you take L2, it will smooth out things. What's going on here is that you don't you are not using any metric. You are using another network which is telling whether it's similar or different. That's the adversarial training trick. And that's something which you can think of as a better critique than using one particular metric to solve the job. So to answer your question, probably it would still outperform UNet. Yeah?
In the cycle gun, we don't have a generator seed. Each image have only one image, one generated image. We don't have a random generation. That's my question. If we have a random seed in the generator or not, directly mapping one-to-one from the image and the generation.
So if I understand your question correctly, you are saying what is the input of cycle gun?
What's input of the generator of cycle gun? It's only the image?
Yes,
and
so
the
it's
or
image to image transfer. So you give it as image as input, you get an image as output.
image. We don't have to, for example, if we change the seed, we get another image.
No, it's different from the original GAN. It's not a noise vector. There is no noise. It's an image.
Yeah. So you are conditioning not on something which is a noise vector as input, as Michael said, but you are conditioning it on the actual input that you are giving, or probably a set. If in more, that's more really the situation. A set that has a particular style. Okay, so there was another question. So, yeah.
Just a small question. Is just about the loss that that are usually used in the cycle. What is the most used loss in this kind of the loss function?
Sorry. Most usually used for
The loss function that are the most used in this cycle of CAN.
So you are asking what sort of loss function is used?
Yes.
So you use the cyclic consistency loss. On top of it, you can also use something like the normal GAN losses. So basically your simple loss function of log expectations of this that you can also use. But
And iteration, number of iteration is included in the loss, or it's not?
sorry?
Number of iteration of the epoch.
Number of iterations. Whether
Included in the loss or not?
no, I mean number of iterations. So when you do an optimization, it's an iterative procedure. At each iteration, you calculate a loss, and you take a gradient step accordingly. You make your you backpropagate the loss, like the gradient of those losses, and then you do it again. So it's a iterative procedure. Those two are two independent things. Here was one question.
Simple question. What is supervised in this?
Sorry.
My question: why do you name synthesis supervised? What is supervised in the method?
Right. so that's a good question. The naming convention. What is supervised here? The supervision here is that you are giving the domains. So it's knowing that it's not a, let's say, real world image or an image taken by, I don't know, from drawn by Van Gogh, but it's only be something that is MR as input and it's getting CT as output. Naming again is a big mess. What you call supervision, what you call semi-supervision, unsupervision, those are still kind of open questions, but yeah, so.
Hello. Okay, as you have said, we have given this only MR input and we have taken the CT output. So in this case, how this network will gonna handle the nonlinear deformations if it happens like in image acquisition time? If some image suppose having some nonlinear deformations, then how this network then is like gonna handle this thing?
So your question is how did, So if I am not...
How it will tackle actually with this non-linear deformations. Suppose some images have some non-linear deformations and some images are correct.
So can you tell what you meant by nonlinear deformation? Is the acquisition problem or...
Is the acquisition problem?
And if they are not corrected?
Yes.
And if you are not conditioning it?
Yes.
Then you answered your question. You don't, because the network doesn't see the difference.
If we just don't make the data set correctly, like if some images are having some nonlinear deformations and some images are correct, so it will not gonna give the CT outputs out correctly also.
No, if you are asking whether garbage in, garbage out is right in this context, yes, that's right.
Okay.
I think that's right for the entire learning context. If you are not, it is to some extent robust to the kind of noises that's coming in, but that to some extent is kind of questionable. It really depends from what sort of problem you are trying to solve.
Yeah.
Yes.
Thanks.
All righty. So I have about 30 more minutes to finish, so I will try to move on the slides quickly now. So now let's look at the next application, which is domain adaptation for adversarial, so domain adaptation using adversarial learning. So this is something which is more common in medical imaging rather than the learning theory or computer vision community. So what's really happening here is that you acquire images and you train your deep neural networks to perform certain tasks, right? So imagine you are trying to do segmentation. Now you have acquired a lot of images and you trained your deep neural network to do well. You have learned that, okay, so it does well, very nice. And then when it comes to a new domain, the performance degrades drastically. So what does it mean by new domain? So for example, you are acquiring MR images. So you have probably 5 or 6 different MR acquisition. And one of them has changed. The rest 5 are same. If you don't retrain your network on that situation, it will typically degrade the performance. So here, Costas has shown this one particular interesting example where they are showing that this is the source domain where they had many different acquisitions which remained similar. And then there was this one acquisition protocol which was GE, which changed to SWI. And they were trying to figure out for traumatic brain injury the segmentation of bleeding and other artifacts. So if you see here in the source domain, the network is performing pretty good. And it's quite similar to what manual annotation was. Now, when it comes to target domain where just one thing has changed and the rest of the protocols are still similar, it's more or less all over the place. And that's the problem they were trying to solve. So domain adaptation is a big problem, especially if it is unsupervised domain adaptation. That is when for the transfer domain, the target domain, you don't have annotations. How do you solve such a thing? So they came up with, again, a very cool twist, which is that you try to learn domain invariant features using an auxiliary task, which is an adversarial task. So before I explain what's really they are trying to do, let me first try to simulate you with the idea of when you just open the paper, what you actually see. So if you are someone like me, when you open the paper, you try to look at the images, okay, to just get a first grasp of what's going on. Now, if you look at the method image of this paper, you are going to see this image. It's probably a bit too daunting, at least for me. When I first when I first have seen it, it has a lot of information that's going on, which is great for reproducing. For the first time, it's probably a bit too tricky. So, but we can actually decipher it. So this is, of course, not typical GAN. This is more of using the adversarial training regime in an interesting twist. So what's really going on here? So you can take this as a block, which you can think of as G. It's not the generator, but really a segmenter. So it takes an image in and tries to predict the segmentation mask of whether it's a healthy or diseased tissue. You can also, if you are familiar with UNet, you can think of this as probably UNet, but this is not UNet they are using in this case. So once that's kind of sorted, now let's try to see what's going on here downstairs. So this downstairs is the auxiliary task, where they are trying to predict the source or target domain. So on all the previous GAN kind of cases before, I showed that you take the output and there you try to predict whether it's true or false, real or fake. Here if you see, the first change is that they are not looking at the final output, but they are taking some small detours in between layers and try to do things. So what's going on here? What's the intuition of this? So the intuition is again quite interesting. So the intuition basically is that if the network is just learning from these images, so it's probably learning a lot of information to segment, but it's also learning information that's related to domain. What we are trying to do is we are trying to take out outputs of these cases and try to predict whether it's a source domain or target domain. If you are successfully predicting it's the domain, that means the domain information is still there. What you really are interested in is to make the representation invariant to the domain information. So you basically train these two together, and the more it fails to predict the domain, the more likely it is that here you are learning representations which are invariant to domain and only necessary for doing the actual segmentation. All right. So that's the really interesting trick. And they have shown some, so of course there are numbers, but I will just quickly show you some of the example cases where without adaptation versus with adaptation, when for the source domain it's perfectly fine, but for the target domain with adaptation things got way better than before. It still misses some of the microbleeding and stuff, but in general it's quite nice. All right. So from the medical application perspective, we are more or less done. So let's move on to the last part, which is more of the emotional part, which are the limitations of GANs and how we can summarize things. Okay. So the first problem of GAN is numerical instability. GANs are too notorious to train. One particular thing that comes associated with this, which is very common in the machine learning lingo, it's called mode collapse. In simple term, it basically means it's predicting one sort of images, typically the sort which it has seen most in the training data, and not predicting the different variations. So it basically didn't learn the actual distributions, but kind of learned the distribution that's there in the training data. So that's the mode collapse. Why such a thing is happening? So again, this is a more theoretical part, but I can give you a bit of an intuition. So I will show you one extreme example of what's actually going on when you are trying to do such a train and how the convergence dynamics works. So this is a very extreme example of what's happening here. So you have a constant curl vector, okay? And this is a non-conservative vector field. So basically that means even though you actually have a minima, you will never gonna reach there. You will keep, like if you just do gradient descent, you will keep on moving around and around forever. All right. The bigger problem is that GAN is a zero-sum game. That's why you have a minimization, maximization in your objective function. And for these zero-sum games, this kind of constant curl vector, this non-conservative vector field appears quite often. That makes GAN quite tricky, quite numerically unstable. As an initial solution, there is this one paper that came out, I think in 2017. It's called Numerics of GAN. So if you are interested in those sort of theoretical details, the numerics details, you can probably take a look at that paper. It's there in the reading list. There are other problems though. Some we already talked about, some we will gonna be talking about, is how do you evaluate? What should be the metrics? When you do classification, it's quite simple. You do accuracy, whatever, dice, F1, you are fine. You are all fine to go ahead. How do you evaluate the quality of the metrics, like quality of the images generated by your network? So one widely adopted solution is to actually pass these synthetic images to another network which has only seen real images and learned how to classify those, and see what the classification accuracies are. If the accuracies are more or less similar, then you can say to some extent that it has learned the same sort of representation that the other convolutional neural networks are learning. But that of course comes with a big problem that your discriminator is also a convolutional neural network. The next one, which should be independent, is also a neural network of same sort. So who will guard the guards? So you are gonna make the same kind of problem and get away with it. There are other solutions. For example, put the images in Amazon Mechanical Turk or show it to a group of radiologists, see what they predict, whether they predict right or wrong, or whether they can predict the difference. Sure, but is it the best possible way to solve this problem? I don't think so. What could be the solution? I am not really sure either. One possibility is to look into some of the literatures of hypothesis testing that people have been doing in statistics for some time, and see what's the minimum number of samples that you need to actually say with some certainty the probability distribution of your real and the synthetic are similar. That's still quite an open problem. There are some limitations of GAN in the practical level though. So I will go into it. So I must give you again a quite bit of a fair warning that you have to you have to go into a diving mode to actually find these solutions. For medical imaging, you won't find such such problems, or it's unlikely that in the web you will find such cases where things didn't happen. There is a significant amount of bias associated with the results that are reported, and most of the times good results are reported. So I basically tried to find some of the results being reported by the computer vision, learning theory community, and tried to guess what would be the equivalent problem in medical imaging. So the first thing is counting. You can see many, many heads, right? So GANs, if you don't provide it conditioning, it's bad at counting. It doesn't understand 1 head, 3 head, whether a person should have how many heads, stuff like that. It's bad at that because it simply didn't learn it. You didn't provide it data to learn. You didn't provide condition to learn about it. A medical equivalent of this could be probably if you are trying to construct cell images, synthetic images, and you don't know what sort of cells should have how many nucleus, stuff like that. Problems can happen. The second one is perspective. You can see here it tried to construct the dogs. You can imagine these might be dogs based on the texture, but the perspective is so distorted that no normal human would call it a dog. No self-respecting convolution neural network should call it a dog either, but that's not the case. That has passed through that test. But if you now try to think of the problems that we were talking about, I think some of the questions were there before. If you are trying to do cross-domain synthesis and it completely forgets what the perspectives are, then that's a bad situation. You really don't want that to happen, and then you can't really plan to do some therapies based on images that generated using such methods. Global structures. Again, we can see dogs if we look at the texture, but where the head is, where the legs are, that's kind of a mess again. Now, if you are trying to do medical image reconstruction, where a significant amount of GANs are used for reconstructing MRs from case spaces or from making low resolution images into better resolution, if the global structure is lost, if the anatomy or how the anatomies are there, if that thing is gone, then it's a big problem, because you don't want to reconstruct and lose what is beside what. That's not the point of reconstruction, whatever fast or however good looking it becomes. So these are some of the problems that's there for GANs. I have also created a reading list for those who are interested into diving further. So these are some of the engineering key GANs that I talked about: DC GAN, conditional GAN, cycle GAN. For the GAN applications, we talked about these 3 papers. But also for our review article, we created something of a living review. So this is basically a tree where you can look at different applications that has used different sort of GANs. And these are clickable, so you can click there and you can get to the actual paper. This comes along with our paper, and I think if you click this link, you can reach there. In terms of theory, those of you who are interested, there are quite a few interesting theory papers going on for the numerics of GANs. Are GANs created equal? F-GANs, where they looked into different divergence measures that come under F-divergence formula and how they are doing. There are also a couple of blog posts from which I look into time to time because they are very nice and explanatory. This of the convex spots is a nice blog post. There is another blog post which is getting a lot of Twitter feed these days. It's about GAN open problems that came, I think, about 2 weeks or so ago. And finally, in the interest of shameless self-promotion, we are also doing a MICHI 2019 tutorial where these paper, like the first authors of these 2 and me, we are going to be talking more about the GAN stuff. So if you are going there in MICHI, probably attend that. So in summary, we talked about something which was originally an unsupervised generative model with an adversarial twist. And we then built on top of it. We showed that unsupervised can be different way of supervised. The particular adversarial twist can be used in many other different applications. And when done correctly, you can expect to see realistic looking images, probably not the hyperrealism that NVIDIA has shown, but it's probably not far away either. In the medical imaging sense, if it's done properly, then it might have a lot of applications in synthesizing proxy for training data. And also when there are cases of domain shift, it has already shown some progress, some interesting directions. There are issues of numerical instability, evaluation metrics, stuff like that. So, in conclusion, the professors and grad students who wants to play with fire, sure, go ahead, give GANs a try. That's a nice firearm for you. All the best to those grad students who will try it because you need that. A lot of times, GANs will backfire and you will be in a horrible sort of mess. If GANs backfire, then probably you should look into the numerics. You should look into the discriminator loss, the generator loss, try to stabilize the discriminator loss. That might be one way to remedy the situation. But when done properly, watch out for the fireworks. Thank you so much for your attention.